Hello and welcome to Graph Mastery Series Day 6. I had my end sems going on, so the series was on a break, but the videos will be consistent from now on and we will complete the playlist for sure. So today's problem is Leetcode 2699 modify graph edge weights. I have assumed you have read the question once and attempted the question for at least 10 minutes. Remember, however hard the question is, you are supposed to try it 10 minutes without any form of technology beside you. So let's start with introduction to problem. So introduction is that we are given an edge list and some of the edges are unknown, which is represented by -1. Not unknown, like we can assign the value to it later. So it is represented by -1 and we can only assign the positive integer value and the range is this from 1 to a very large number. And we need to find the shortest distance between, no, we need to return the edges such that the shortest distance between the source and the destination node becomes equal to an integer target which is also given. So if you are confused, let me be very clear that you will be you will get the clarity when I will explain you the example, so just hold on. So yeah, this is the question and we are given some of the edge weights are given and some of them are currently not assigned, which is represented by -1. And we have to change the weights of -1, like we have to assign the -1 such that uh, the shortest distance between the source and destination becomes equal to target. Target is also given to us. And yeah, we have to finally return the edges array. And if it is not possible to make the shortest distance between the source and destination equal to target, then we will return an empty array. Yeah, so this is all we need to do. And one thing which is, I think you should know it till now, that please make sure how the output list is there. Like we are supposed to return the edges and all the edges and just the -1 edges need to be modified. And yet all the edges need to be returned. So this should be done by you while attempting the question for 10 minutes. Okay. So this is done. Obviously, prerequisite to the problem is like written very clearly, very broadly. It should be known that it is a Dijkstra question and Dijkstra is a prerequisite to this question. Dijkstra's algorithm should be like done by you. Then you would be able to solve this question. Okay, so let me tell you about the series firstly before starting. Today is day 6 of our beginner to mastery series. So let me give you a brief. What Striver or other coding sheets does is take you from level 0 to a beginner level. But this is not enough for strong companies or for big companies nowadays. You need to gain confidence will take you from a beginner to mastery level. So if you know the basics of all the algorithm, currently we are doing the graph series, so if you know the basic beginner level of all the algorithm in the graph, we will take you to the mastery and will help you gain the confidence totally. Today is day 6 and we are covering Leetcode at 2698. Okay, so let's start with the problem. Intuition is obviously very clear. The shortest weight needs to be found out. So obviously it is a Dijkstra's problem. Most obviously it is a Dijkstra's problem. Okay. And second thing, which it is not mentioned here, but if you have read the question, then you should know that the constraints are very relaxed. Constraints are relaxed. So that means that we are allowed to run loops or run algorithms like a few amount of time. Like maybe we can run Dijkstra and loop or something like that. We need to think about it, what is actually needed. And this is actually a good question. This is not very easy question as compared to other hard question. This is also in the list of medium to hard, in the hard category itself. Okay, so let's start with the example. So let's take this example. Let me change the pen color. Okay, so let's change. We are given the graph. 0 is the source and 4 is the destination, and some of the edge weights are unknown, which is -1, and some of the weights are, one of the weight is known, which is 4. And we need to make the target equal to 70. So what we can do, like intuitively, if you think, you need to just make all the weights 1 and the final weight which should be made equal to whatever is left. Like you can make it 64. How we will make it, we will know in detail. Firstly, you should know that make all the weights 1 and the last -1 should be changed to the like required value. So yeah, this is the solution to this problem. This is the humanistic approach. We will note how we can code this. So yeah, all the weights to -1 and finally to 64. The shortest path becomes 1 plus 4 plus 1 plus 64, which is equal to 70. And this is the only path in this question. Now let's consider the example 2. So we are given a graph and our target is 7 and our shortest path currently is 9. But if we upgrade this -1 to 4, then our shortest path can become 7. So this is an example. Uh, I will tell you why it is relevant in when I further explain you the try run and approach. Now this is the example 0. I forgot to tell you this, but there would be no problems now. So what example 0 is that you are given a graph. The target is 9 and the shortest distance currently is 9. So what you are supposed to do? The shortest distance currently is 9. So you don't need any more. Like uh, uh, you can simply change all -1 to int max or whatever the max values they were, so that the shortest distance remains same and it doesn't matter. So you can change it to 2e9 as given in the question. The shortest distance remains 9, and make sure that the graph can also be like this 4 and 7. Still the shortest distance would be 9. Here the shortest distance, like here the distance would be 11 and here it would be 9. The shortest would be 9. And yeah, initially don't consider an edge wherever there is a -1. So just calculate the shortest distance of the constants. So you will get 9, and if it is equal to target, you will make all the variables as 2e9 and return the edge list. Finally, the last example. I think this would be enough to go to try. The last example is, let's say we have a graph. Uh, this is source, this is destination, and here this is 7, it's 2, 2, here it is -1 and -1, and our target is equal to 5. So as I told you, firstly you are supposed to find the shortest distance using only the constants. You will not use the -1 which this will be not used, and what you will get, don't be confused, you will get 4. Because the shortest path shall go. This is a prerequisite of Dijkstra, so let's not waste time here. You will get 4. Now the current shortest path without the -1 is already less than the target. So whatever value you assign to it, you will never reach the target because there's already a shorter path which doesn't have a variable length. So that means there will always be a path less than target. However much you can change this, you can change this to 1 1, but this won't be equal to target. If you change this to 3 2, it would be 5, but the shortest path still would remain this. So in this case, you have to return an empty vector. So there are two learnings from our examples. One is firstly you need to calculate the constant. Using constant distance only, you need to calculate the shortest path, and if the shortest path is equal to the given target, then make all variable edges, that is equal to all -1 edges, to int max, oh sorry, 2e9 as given in question, and return the edge list. Else, no, not else, if shortest path is less than the target, that means the shortest, like the constant distance only has less than target. So whatever changes we make to the variable edges, -1 edges, there won't be a shorter path. So you can simply return an empty vector because the answer is not possible here. Okay, so now let's build the code here from here on. So let's say we are given, let's take this example, or I will modify it a bit to help you more. So we are in the dry run currently. So we are given a source edge. From the source edge there is constant path of 4 and 2, and here we reach destination, and then we have a variable path of 5, sorry, constant path of 5 and a -1 and a 4, and another path -1, 2, -1 and -1. Okay, so we are given this and our target is 7. So what you are supposed to do is, yeah, I know this is hard to find out, but if you keep on practicing, you will surely understand, you will surely know how to find it out, like without seeing the solution. So currently what you are supposed to do is you only you remove all the edges from -1, like don't even build an edge wherever there is a -1. So your graph would become something like this. 2, there would be a disconnected component here. And find the shortest path from source to distance in this array. Now the shortest path from source to distance in this area is 4, 2, which is 6, which is less than target, and it bypasses the both two criteria mentioned above. It is not equal to target. Sorry, let's say this is 8. Let's say this is 8. So the shortest path is currently is 12. So it bypasses both the criteria. It is not less than target and it is not equal to target also. So yeah, so now we can move to the algorithm. So firstly calculate a constant part and store it in a variable. So you have a constant part s is equal to 12. Then iterate through the edge list, and whenever you find a -1, change this to 1. As I explained above, the intuition is to change all the -1 to 1, and whenever there is a, like we need to change the final -1 to whatever the value is needed. So change the -1 to 1 and again find the shortest path. Changing this -1 to 1, we would get, let's say we encounter this -1, we can encounter any of the -1 as like it totally depends on the order of edge list which is given to us as input, but the answer would be same in every case. So let's say we encounter this -1 and then we change this -1 to 1, add to graph, and then again calculate the shortest distance using Dijkstra algorithm. Here also shortest distance was calculated using Dijkstra algorithm. So for this graph, calculate the shortest distance from source to destination. Again, that answer would be same, so we would continue our iteration, no changes. Let's say we find this -1. Again, the graph would change like this, yet the shortest distance would remain 12. So the shortest distance is still equal to constant distance. So there's no change because the source and destination hasn't been connected. Okay, so we are done till here, and then let's say we find this -1. Even if we find this -1, the shortest distance would still remain. The shortest distance would change. Okay, let's assume we find this -1. Let's assume before this -1, which would give us our answer, we find this -1. We change it to 1. And then our graph would become like this. The shortest distance would become equal to 10, which is less than the constant distance, which was 12. So now we'll look if the shortest distance currently, new shortest distance, which is found using the Dijkstra algorithm, is less than equal to target or not. We need to say this if the new shortest distance is less than equal to target or not. Because if it is greater than target, then like there is no point, like we can't change this path to be equal to target because we are assigning the minimum value to each variable node. So however much we try to change, we will not be able to reach the target. So if it is greater than target, we would totally ignore the path. Like we will continue our iteration. We will make this one and continue our iteration. If it is less than target, okay, we will see the less than target case here. Now currently our graph is like this. This is 4, 8, destination 1, 2, 1, and here we have a -1 currently, and here we have 5, 1, 4, and our const shortest path was 12, and our target is equal to, how much was the target? Sorry, so our target was equal to 7. Now finally we come to this -1. So this -1, we would change it to 1. As in all cases, currently we would change it to 1 firstly. Okay, and then calculate the shortest path from source to destination. Now you can see that the shortest path becomes this one. Oh. Now you can see the shortest path becomes this one. And the shortest path value is 2 plus 1 plus 1 plus 1, that is equal to 5. So new shortest path value is 5. Now notice that the new shortest path value is less than target. That means this is where our answer lies. This is where our answer lies. We simply need to change the last node to another value, last change node to another value, and we have our answer. So what we can do is we need to change the last node to the current shortest path, like target minus current shortest path minus 1. Sorry, target minus current shortest path plus 1. So the target is 7 and our current shortest path is 5. 7 minus 5 would give us 2, and we change it to plus 1, which is equal to 3. This is basic maths. if you like use copy a pen or apply a bit of brain, then you will know why we are making all edges to 1 and finally why we are changing to this. So this becomes 3. So now this edge weight has become 3 and the shortest path value has become 1 plus 2 plus 1 plus 3 which is equal to our target 7. So yeah, this was the overall algorithm. I hope you understood it. Let's write it in text. That how it works. Let's write it. Try to code it at this point after I have written the algorithm text. So firstly find constant distance using only the constant weights, like ignoring all the -1 weight. And yeah, obviously you have to use the extra every time to find the shortest distance. Okay, now if you can check the two conditions mentioned above. If it is equal to target, the shortest distance, const distance is equal to target, then make all -1 edges as maximum to eliminate the path. Because it can give a smaller path if we make all the variable length to 1, then it can give a smaller path. So to eliminate the path, we will make it 2e9 and we'll have our shortest path equal to the equal to target. If it is less than target, if the constant path is already less than target, then that means our shortest path can never reach target because there's a constant distance, like no changeable distance is already less than target. So in this case, return empty. This is like kind of a pre-check before question. Now iterate through the edge list. Iterate through the edge list uh, and as you find a -1, whenever you find a -1, update the adjacency matrix and change it to 1 as we saw in the dry run example. So we change every -1 to 1 and then again calculate the shortest path. If the shortest path is less than target, that means that it is it is able to form our target as the shortest path. If it is greater than target, then we don't have to do any operation. But if it is less than target, then all we need to do is change the edge weight is equal to target uh, target minus current shortest path plus 1, and this would make the final weight as like whatever is required and then return the answer adjacency list. I hope you understood. If not, I will try run the algorithm for one final time because I think the question is a bit complex. So let's try run it for one final time. So this is given -1 4 -1 9 8 and target is equal to 10. So firstly, I'm going a bit quick this time because I've already explained this. So firstly, we find the const distance. Currently, our graph looks like this only 9 8 and there's a uh, yeah, this is the oh sorry, forgot to mention the source and destination. This is the source and this is the destination. So we would start from here and the destination is here. So only path is here. So const distance is equal to 70. Bypasses all the both the checks mentioned in the algorithm. So we would move further. Now we will traverse this list, find the first -1 edge, convert it to 1. So now our graph looks like this: 1 4. So now our graph looks like something like this: 9 8. Source destination 1 4. Yeah, this is still -1, so we are not currently adding this. So now we again find the shortest distance between source and destination. It's still 17. It is not less than target. So we continue our iteration. Now we find another -1 edge. As soon as we find a -1 edge, we change it to 1. And again find the shortest distance. So this time the shortest distance comes out to be 6. Now 6 is smaller than the target. 6 is less than 10. So this is our ideal path. What we will do is we need to finally change the value of 1. So how we would update is that 10 minus 6 plus 1. I already mentioned it, the target minus current shortest distance plus 1. So this would be updated to 5. And hence our shortest path becomes 5 plus 4 plus 1, that is equal to 10. This path yields 17, so this path is rejected. And yeah, finally update the edge list vector and this is our final answer. So I will explain the code. Let's see. So this is the code of Dijkstra algorithm. I hope you know this. This is like the basic of Dijkstra algorithm. Okay, and yeah, you can use a data structure instead of, this is an upgrade from the normal Dijkstra algorithm in terms of code readability. You can use a DS instead of writing again and again the this whole thing. You can directly write DS and the priority queue works. Then firstly, if you are given an edge list in this format, I already mentioned you should see the question. You need to create the, if it is not equal to -1, so we are creating edge list only consisting of constant values. Then we find the constant distance using Dijkstra algorithm as mentioned, and if then the two checks are here. If it is less than target, if the constant distance is less than target, then we need to return an empty array. If it is equal to target, then for every -1 we are changing into int max value. Max value is defined. We are changing into max value so that to eliminate the path. And then if both the checks are bypassed, then we move further in our algorithm. Now we create an answer vector of vector, which is edges, which is currently whole of this. Currently we have whole of this as our answer. And as we found, yeah, we can maintain answer found variable. So why it is there, I will explain you. Let's say we have found the answer here. The answer has found out to be 10 here. And there's another path which has a -1. And this would be updated to 1 and 1 again, although we have already found our answer. So if answer found is equal to true, then we don't need to change these values. We need to simply assign the max value to it, 1e9, 1e9, so that this path gets eliminated and this path is selected for the shortest path if the answer found variable is true. So if the current is -1 and answer is not found, so we change it to 1, update the adjacency list and get the new distance. Change the -1 to 1 and get the new distance. If the new distance, this if is redundant, this is my old code, so yeah, you can skip this if. So if the new distance is less than target, let me explain why this if is redundant, because we know const distance is already greater than target, so you can directly write this if. Like if this is passed, then this is already passed, so you don't need to write this. So if the new distance is less than target, that means we have a path which can form our target, and here we change the value of the final one to the, like I mentioned, target minus new distance plus 1, and set the answer found to true because I've found our answer. So yeah, what we did is changed the all the -1 to 1 iteratively, and when we found our answer, like the final -1 connecting, like when we found our final -1 connecting the path, there let's say 1 1 1, we got so many -1, and when we find the final -1 connecting the path, we firstly make it 1, see if it is connected. It is connected, it will give a shorter distance. Then we change this value to the required value, which is target minus new distance plus 1, and we have hence all the -1 becomes 1, and all the and yeah, the final -1 becomes the required value. And if it is a variable length and answer is found, as I mentioned, answer is already found, so we need to eliminate the path. We need to make it, change it into max val. So this will eliminate the path, like as I explained here. Let's say our answer is already found, -1 -1. We have changed this to make find our answer. Then there's, to eliminate this -1, we would simply change it to 2e9. How we are finding that answer is already found? Using the bool answer found variable. If it is true, we change the -1 to 2e9. And then finally we return our answer. If answer is not found till the end, then we return empty vector. This is a final safety check. And then ultimately we return the answer. So yeah, basically we are only concerned with the constant edges in this for loop, and from here on we are only concerned with the variable edges. Yeah, so yeah, here we got the new Dijkstra distance, and if it is less than target, we update the, like the final -1, as I mentioned. Let's get to the time complexity. I've already made ChatGPT do it. So what the time complexity is, that we are iterating through all of the edges, which is, let's say, at n size, and for every edges, at the worst case, we are running Dijkstra algorithm for each edge, because we are running Dijkstra algorithm again and again. After making the -1 edges 1, we are running the Dijkstra algorithm again and again. So time complexity becomes n square, n into n log n. N log n is for Dijkstra. So ultimately it becomes n square log n. N square log n. And the space complexity here is obviously big O of m plus n, because we are using vector of vectors and all. Yeah, so that's all for this code. Thanks for watching.